On a quiet night like this, it is easy to believe the world outside your window is stable and familiar. The temperatures rise and fall with the seasons in a rhythm that feels ancient and reliable, as though the earth has always offered this kind of gentleness to the living things on its surface. But that feeling, however comfortable, is not the truth. It is a brief interval of warmth borrowed against a much longer, colder story. And that story has been running long before human beings were here to notice it. Over the last million years, ice has advanced and retreated across the northern hemisphere, not once, not twice, but in a repeating pattern that makes our current warm period look less like a permanent condition and more like a pause. Great sheets of ice, in places 3 kilometers thick, have buried North America, is stretched across northern Europe, and pressed down across large portions of Asia. The world we know, with its open forests, its farms, its cities, exists on ground that was, not so long ago in geological terms, sealed beneath a weight of frozen water tall enough to swallow almost everything we have ever built. And then it melted, and the world warmed, and life crept back, and then it froze again, and then it melted again. That cycle, slow and enormous and indifferent, is the rhythm underneath the one we think we know. The warmth we are living inside right now, this period that stretches back roughly 11,000 years and that scientists call the Holocene, is not a destination. It is an inhale, a brief, bright pause between long, cold exhales that have defined most of the planet's recent history. And if you feel a slight unease hearing that, hold on to it. It is a useful feeling because it pushes us toward a simple, unsettling question. Why? If you enjoy videos that challenge the way you see the world, consider subscribing. It helps more than you might think, and I genuinely appreciate every one of you who chooses to come along on these journeys. Settle in, get comfortable. Let us begin. Why does the planet do this, and how do we know it is not just a story someone has assembled from a few dramatic-sounding facts, stitched together into a pattern that feels compelling but might be, at bottom, an illusion? Those are fair questions. They deserve serious answers. But before we get to the evidence, before we look at how scientists actually know what they know, there is something that needs to happen first. That you need to feel the scale of what we are talking about. Not just understand it in the abstract, the way you might understand that the universe is large or that history is long, but actually feel it in the way that only a slow, careful reckoning with the numbers can produce. So picture the ground beneath a major city, not an ancient city in the tropics, but something you likely have some sense of. New York, London, Berlin. Cities built on temperate ground, cities with stone and steel and deep foundations, cities whose soil holds the compressed residue of centuries of human life. Now picture ice forming on that ground, not a snowstorm, not a hard winter, but ice that does not melt when spring arrives, ice that persists through the following summer and is joined by more snow in the following winter. Ice that, a year by year and century by century, builds on itself the way a very slow, very cold tide that never fully retreats will eventually submerge a coastline. That is how ice sheets grow, not in a single dramatic event, but in an accumulation so gradual that no single year would feel catastrophic to anyone living through it. And yet, the accumulation continues, and the weight increases, and eventually the ice above a city like Berlin, or above the valley where London now sits, reaches a thickness of 3 kilometers. 3 kilometers. It is worth staying with that number rather than moving past it. 3 kilometers is roughly the cruising altitude of a small aircraft on a short regional flight. If you have ever looked out of a plane window just after takeoff and thought to yourself that the ground already looks impossibly far away, and that the cars have shrunk to the size of insects and the buildings look like toys, you are probably somewhere between 1 and 2 kilometers up. 3 kilometers is above that. 3 kilometers is the point at which the horizon begins to curve just slightly in your perception, where whole counties and provinces are visible at a glance. And that is the height not of the sky above these cities, but of the ice pressing down on them. Ice sitting on the ground where those cities stand, rising higher into the air than most small planes bother to climb. Not a glacier in a distant mountain range, not a remote and exotic feature of the polar world, but ice resting on the particular piece of ground where, in our current warm interval, millions of people go to work and cook dinner and fall asleep. And it was not thin, fractured, unstable ice that would crack under its own weight after a few 100 meters. 3 kilometers of ice is ice that has been compressed by its own mass into something dense and slow and almost geological in character, ice that flows under pressure the way very thick, very cold honey might flow, grinding the rock beneath it flat, scouring valleys deeper, reshaping the landscape in ways that are still visible today. The hills outside of New York, the flat agricultural plains of northern Europe, the particular shape of the Thames River Valley, these are not natural accidents. They are the carved-out remnants of a world that ice remade. And the ice did not merely alter the land, it pulled enormous quantities of water out of the global ocean and locked that water away in frozen sheets across the continents. Sea levels dropped to the point where land bridges emerged between places that are today separated by hundreds of kilometers of open water. The coastlines of the world shifted outward in every direction. Shallow seas drained. Entire continental shelves, now submerged beneath the ocean, were dry land where animals walked and rivers ran to the sea from endpoints that no longer exist. The world, in other words, was not just colder, it was a different physical shape. Now hold all of that. The ice 3 kilometers deep, the cities buried, the coasts reshaped, and add time to it. Not one episode, not a single cold event that lasted a long while and then ended. Over the last million years, this cycle has played out repeatedly, in a rhythm that once you see it feels less like a series of separate disasters and more like something the planet is doing on purpose, the way a living body draws breath. The planet spends roughly 90,000 years cooling down, with ice advancing slowly from the poles and from the mountain ranges outward, grinding, accumulating, locking up water, lowering sea levels, reshaping coastlines. Then, in what geologists consider a startlingly brief interval of perhaps 10,000 years or less, temperatures climb sharply, the ice retreats, sea levels rise, and the world opens back up into something like the conditions you are living in right now. And then it cools again, and then it warms again, and then it cools again. This is what it means to talk about the planet breathing, not as a metaphor chosen for emotional effect, but as an honest description of what the geological record shows. Long, cold exhales lasting 9 times as long as the warm inhales that follow them. If you imagined this rhythm as a breath, it would be a breath so prolonged and so extreme that the inhale, the brief warm interval, seems almost accidental by comparison, a gasp between long, slow releases. The warmth is not the story. The cold is the story. The cold is the pattern into which the occasional warm interval briefly intrudes before the planet exhales again. Something is keeping time here. Some force or combination of forces is driving this rhythm, acting as a kind of hidden metronome that tells this planet when to freeze and when to thaw, repeating its count with enough regularity that you can trace the same basic beat across 10 cycles, across 1,000,000 years of record. That regularity is not something we invented to tell a compelling story. It is there in the data, waiting to be read. And learning how scientists actually found that data, how they pulled the evidence for these cycles out of the Earth itself, is where things begin to get genuinely strange. That search leads us to one of the quietest, most hostile places on Earth, the high Antarctic plateau. Picture it, a continent sitting at the bottom of the globe, buried under ice so thick and so ancient that the bedrock beneath has been pressed downward by the sheer weight pressing on it from above. The plateau itself sits at an elevation of roughly 3.5 kilometers above sea level, which means the air is thin. The cold is extreme even by polar standards, and the silence is the kind of silence that feels less like an absence of sound and more like a physical pressure against your ears. This is not a place that invites investigation. But this is exactly where the evidence was waiting. Start with what accumulates here. Snow in central Antarctica almost never melts. There is no spring thaw, no summer rain washing things away, no river carrying sediment to the sea. Year after year, snow falls on snow. Each season deposits a thin new layer on top of everything that came before. And as the layers deepen, the weight of all that accumulated snow begins to press down on the layers beneath. The crystals are squeezed together. The air that was once woven through the loose snowflakes is slowly pushed out, or trapped in pockets so small you would need a microscope to see them. And the soft, airy powder that fell in a blizzard thousands of years ago becomes, under that sustained pressure, dense, clear ice. Ice that still contains, sealed within it, tiny bubbles of the atmosphere from the moment those snowflakes first settled. Now consider what nearly 4 kilometers of that material represents. The ice sitting at the center of the Antarctic plateau is close to 4 kilometers deep in places. Not a cliff face you can see from a distance, but a vertical column of frozen time stretching from the surface where a researcher might stand today, all the way down through layer after layer of compressed snowfall. Each layer a year, each year a thin band of chemical information and trapped air, until you reach ice so old it formed long before anyone was alive to wonder about it. Nearly 4 kilometers. And to travel that distance vertically, in an elevator moving at a moderate pace, you would be riding for several minutes, watching the floors count upward or downward, and every single floor would represent years, decades, centuries of snowfall. All of it preserved, all of it waiting. That is what the ice is. It is not simply frozen water. It is an archive, a physical object in which the history of the atmosphere has been recorded in sequence, layer by layer, from the most recent to the most remote. Getting into that archive required drilling. Teams of researchers working at Soviet and then Russian stations at a site called Vostok deep in the East Antarctic interior spent years lowering equipment into the ice, pulling up cylindrical cores of frozen material, handling them carefully so that nothing was contaminated, and storing them at temperatures cold enough to preserve the bubbles inside. What they eventually extracted pushed the climate record back roughly 400,000 years, further than any direct measurement of ancient atmosphere had reached before that point. Then, at a different drilling site called Dome C, as part of a project called Epica, teams pushed further still, extracting cores that reached back through roughly 800,000 years of continuous snowfall, making the Antarctic plateau the single deepest archive of atmospheric and climate history available to science anywhere on Earth. Sit with that image for a moment. You are holding a column of frozen air that is older than our species. Each bubble is a tiny capsule of atmosphere from a world that no longer exists, and the air sealed inside the deepest layers of those cores was moving through the lungs of animals whose descendants have not yet appeared in the fossil record. It was drifting over coastlines whose shapes have since been entirely remade by the rise and fall of sea levels. When that air was new, the ice sheets that later buried northern Europe had not yet begun to advance. And now it sits inside a core of clear ice, extracted by a drill, catalogued on a shelf in a cold storage facility, available to be measured with instruments precise enough to reconstruct the concentration of gases in an atmosphere that no human ever breathed. The measurement itself is, in a sense, the simplest part of the process. Once the cores are in the laboratory, scientists can release the trapped air from the bubbles, analyze its chemical composition, and extract from that composition an estimate of the temperature at the time the ice formed. Because the ratio of certain isotopes in the water molecules of the ice itself shifts in predictable ways with temperature, providing a second channel of information alongside the trapped gas. Two separate signals locked into the same physical object, one from the ice and one from the air inside it, both encoding the same moment in the past, both available to be read by anyone with the right instruments and enough patience. The cores were drilled, the bubbles were measured, and when the data came out of the computers and appeared as a line on paper, it did not look like noise at all. It looked like a machine. Not approximately like a machine, and not loosely similar to one in the way that a repeating pattern might remind you of a mechanism if you squinted and were generous. It looked, with very little ambiguity, like something that had been built. What came out of those calculations when the ice core measurements from Vostok and then from Dome C were assembled into a single coherent record and plotted against time, was a line that moved in a way no one had fully anticipated seeing with such clarity. The expectation, the reasonable, defensible, scientifically honest expectation, had been that the data would be complicated, that it would contain signal, yes, but that the signal would be buried inside noise, partially obscured by local effects, regional variations, the countless small disturbances that accumulate over hundreds of thousands of years. A climate is a system of enormous complexity. Oceans move heat around the globe in ways that are still being mapped. Volcanoes inject material into the atmosphere on no predictable schedule. Vegetation shifts, currents reorganize, and dust patterns change with the arrangement of land and sea. Given all of that, a clean pattern would have been surprising. A pattern this clean seemed, at first glance, almost impossible. But there it was, a line that climbed slowly, very slowly, over tens of thousands of years, and then dropped sharply back down in what amounted, on that timescale, to a nearly vertical cliff. Then it climbed again, then dropped, then climbed. The shape had a name, and once you hear it, you cannot unsee it in the data. Researchers called it a sawtooth, and if you hold a carpenter's saw in your hand and look along the length of the blade, you see a row of teeth, each one slanting gradually up from its base and then dropping steeply from its tip. That is what the temperature record looks like across 800,000 years. Each tooth is one glacial cycle. The long slant upward is not the warming, it is the cooling, the slow, grinding accumulation of ice over roughly 90,000 years. And the sharp drop from the tip back to the baseline is, counterintuitively, not a collapse, but a recovery. The short, fierce warming that ends each glacial period in a geological instant, over roughly 10,000 years or less, before the slow cooling begins again. The geometry of the sawtooth is the geometry of the Ice Age cycle, and the Ice Age cycle is the geometry of the planet's recent history. 8 of these teeth are clearly visible in the record. 8 complete cycles, each one beginning with a world not entirely unlike the one we know, and ending in a world buried under ice kilometers thick, and then snapping back toward warmth before the long descent begins again. You can count them. They are not hypothetical. They are not inferred from ambiguous signals. They are there on the page, one after another, spaced with a regularity that took some time to fully absorb. The spacing between the warming spikes, from one sharp peak to the next, is approximately 100,000 years. Not roughly 100,000 years in the way that an estimated distance is rough. 100,000 years with a consistency that, when you measure it across all 8 cycles, it produces an average so close to that figure that the variation feels less like noise and more like the tolerance of a well-made instrument. And then there is the second signal, the one carried by the air trapped inside the ice rather than by the ice itself. When the scientists released the gas from those bubbles and measured the concentration of carbon dioxide inside, they found that it did not behave independently of temperature. It moved with temperature. When the temperature record descended into a glacial period, carbon dioxide concentrations fell alongside it. When the temperature snapped upward into a warm interglacial, carbon dioxide rose in the same movement, on the same timescale, in the same direction. 2 separate physical systems, the thermal state of the atmosphere as recorded in the isotope ratios of the ice, and the chemical composition of that atmosphere as preserved in the bubbles, traced the same line. The sawtooth appears in both channels. You are not seeing one measurement of one thing. You are seeing 2 independent measurements of 2 different things arriving at the same answer, cycle after cycle, for 800,000 years. The details of what drove what, whether temperature led carbon dioxide or carbon dioxide led temperature, and by how much and through which chain of causes, are questions that scientists have spent decades working through carefully. And the answer involves feedbacks rather than simple, linear causes. But that question, important as it is, comes slightly later in the story. What matters in this moment is simpler and more striking. These 2 signals move together. They are coupled, yet whatever is controlling the rhythm of the ice ages is doing so in a way that links temperature and atmospheric chemistry into a single coordinated response, and that response has a period of approximately 100,000 years, and it has repeated without interruption for as far back as the record reaches. That realization is both comforting and disturbing. Comforting because the pattern is clear, cleaner than the complexity of the climate system would seem to allow, cleaner than almost any long-term geophysical record has a right to be. Disturbing because a pattern this regular, this mechanical, this utterly indifferent to the chaos you would expect to drown it out, demands an explanation of a very specific kind. A random process does not produce a sawtooth. A noisy, complicated, a feedback-driven system does not repeat the same cycle 8 times in a row with 100,000-year spacing unless something external is imposing that rhythm on it. Something is setting the pace. Something is marking the intervals. What sort of clock has the power to freeze continents on a schedule? The question hangs there, and the first instinct is a reasonable one. If something is keeping time inside the climate system, you might expect the timekeeper to be inside the Earth itself. The planet is not a passive object. It has a molten interior that drives volcanic eruptions, pushing carbon dioxide into the atmosphere in pulses and surges. It has ocean currents that carry heat from the tropics toward the poles and cold water back down into the deep, circulating on timescales of centuries and longer. And it has the slow movement of tectonic plates grinding continents together and pulling them apart, reshaping coastlines and mountain ranges over millions of years, all of which affects how air and water move around the globe. Any of these processes could, in principle, produce a rhythm. Any of them could, in principle, set a pace. And so scientists did not leap immediately to an exotic explanation. They went looking first in the obvious places. The honest answer is that for decades, no one could say for certain What was keeping time? The candidates from inside the Earth did not match. The clock, it turned out, was not inside the planet at all. It was above it. Volcanic activity does produce long-term fluctuations in atmospheric carbon dioxide, and those fluctuations do influence climate over millions of years. But volcanic output does not pulse on a 100,000-year schedule. When researchers mapped its variability against the ice core record, the rhythm simply was not there. Ocean circulation is similarly irregular. It shifts and reorganizes in response to changing conditions. But it does not impose the conditions. It responds to them. It is more like a pipe that carries water than a pump that decides how much water to move. A tectonic drift operates on timescales of tens of millions of years for any single meaningful reshaping of geography, which makes it entirely the wrong speed to explain cycles running at 100,000 years with machine-like regularity. These are interesting processes, important processes, processes that shape the background conditions of the climate in profound ways. But none of them is a clock. None of them produces a steady repeating interval. And the interval in the ice core record is so precise, so geometrically consistent across 8 full cycles that only an actual clock can explain it. So where do you look for a clock that operates outside the planet? You look up. You look at the orbit. The Earth is not sitting in a fixed position relative to the Sun, moving in a perfect circle, holding perfectly still on its axis. Its orbit, its tilt, and the direction its axis points are all slowly changing, driven by the gravitational pull of the other planets in the solar system, most powerfully by Jupiter and Saturn, the 2 largest, whose combined mass dwarfs everything else in the solar neighborhood except the Sun itself. These 2 giant planets are not close to Earth, but gravity does not require proximity. It requires mass, and Jupiter and Saturn have it in enormous abundance, and over long timescales, their gravitational influence accumulates into systematic, measurable effects on Earth's orbit and orientation. What that produces, when you work through the mathematics, is not 1 cycle, but 3. The first is called eccentricity. It describes the shape of Earth's orbit around the Sun. At some points in the cycle, that orbit is almost perfectly circular, and meaning Earth stays at roughly the same distance from the Sun all year. At other points, the orbit stretches into a more elongated ellipse, meaning Earth swings noticeably closer to the Sun at one part of the year and farther away at another. This stretching and relaxing is driven primarily by the gravitational tug of Jupiter and Saturn working on Earth's path over long periods of time. The period of that cycle, the time it takes for the orbit to go from nearly circular to elliptical and back again, is approximately 100,000 years. That number should stop you. That is the same number the ice cores produced. That is the same spacing visible in 8 complete cycles of ice ages and warm periods. The match is not approximate in the way that a rough guess might accidentally come close. It is the same clock. The second cycle is called obliquity, and it describes something different. Not the shape of the orbit, but the tilt of Earth's axis. Right now, that axis is tilted at approximately 23.4 degrees relative to a line perpendicular to the orbital plane, which is the familiar angle that gives us our seasons, tipping the northern hemisphere toward the Sun in summer and away from it in winter. But that tilt is not fixed. It rocks slowly back and forth, like the slow nodding of a large, heavy object that has been nudged slightly off-center, cycling between a more upright orientation and a more leaning one over a period of roughly 41,000 years. When the tilt is larger, the seasons become more extreme. Summers receive more intense sunlight, and winters become deeper. When the tilt is smaller, the contrast softens. And the period of that rocking motion is 41,000 years, and that period also appears in the geological record of past climates, detectable in sediments and ice cores as a secondary pulse beneath the dominant 100,000-year beat. The third cycle is called precession. It describes not the angle of the tilt, but the direction the axis points. Earth's axis behaves like a spinning top that has been set turning with a slight lean. It does not fall over, but the direction of that lean rotates slowly around a full circle, completing one rotation in roughly 23,000 years. Today, the North Pole points toward the star Polaris. In about 12,000 years, it will point toward the star Vega. This slow coning motion changes which hemisphere faces the Sun during which part of Earth's orbit, which changes the timing and intensity of the seasons in each hemisphere across thousands of years. And 23,000 years is a period that, like the others, appears in the geological record. The signal is there in deep-sea sediments, in layers of dust, and in the isotope ratios of the ice cores. Taken together, these three cycles, eccentricity at roughly 100,000 years, obliquity at roughly 41,000 years, precession at roughly 23,000 years, describe a set of slow, overlapping rhythms imposed on Earth's orientation and path through space by the gravity of the solar system's largest planets, reaching across hundreds of millions of kilometers to tug on this one. The precision of those cycles and the way their periods echo through every long-term climate record that has ever been produced is one of the more quietly extraordinary things in science. The solar system's gravity reaches across that distance and leaves its fingerprint in ice. But here is the puzzle that troubled scientists for decades. These orbital shifts change the amount of sunlight reaching high latitudes by only a small percentage. That is not enough energy to freeze a continent. Something else must be at work. Something else must be at work. And to understand what that something else might be, it helps to first sit with the achievement of the timing itself, because the precision of the orbital prediction deserves more than a passing mention. It deserves the weight it has earned. There was a man named Milutin Milankovich, a Serbian civil engineer and mathematician who, in the years around the First World War, has set himself one of the most impractical tasks in the history of science. He decided that he would calculate, entirely by hand, the amount of solar radiation reaching different latitudes on Earth across hundreds of thousands of years. Not because he had a telescope or a drilling rig or a laboratory. He had pencil, paper, and time. And for a portion of that period, he had those things in very constrained circumstances. He was in Budapest when the war broke out, and as a Serbian national in Austro-Hungarian territory, he was briefly placed under house arrest. He used the time to calculate. The image that remains is not of a prisoner pacing and waiting, but of someone sitting at a desk, filling notebooks with numbers, working through a problem whose answer no one would be able to check for decades, yet because the tools needed to check it did not yet exist. Milankovich was focused on what happened to sunlight at high northern latitudes, particularly in summer. His reasoning was careful and, in retrospect, exactly right. For an ice sheet to grow, you do not necessarily need winters to become dramatically colder. You need summers to become cool enough that the snow falling through the cold months does not entirely melt. If summer sunlight weakens enough at the right latitudes, the previous winter's snow survives into the following autumn. The year after, a little more survives. Over centuries and millennia, what was once bare ground in August becomes a surface that is always white, always reflective, always cold. The threshold that matters is not how cold the winters are. The threshold is how warm the summers fail to become. And Milankovich calculated, across the three overlapping orbital cycles, the slow stretching of the orbit, the rocking of the tilt, the coning of the axis, how that summer sunlight at high northern latitudes had varied across several 100,000 years of Earth's history. He produced a set of curves, rising, falling, falling, a prediction, written in a notebook in wartime, of what the actual climate record should look like if the orbital hypothesis was correct. This is worth pausing on. A man with pencil and paper, under house arrest, predicted the shape of a climate record that would not be measured for another 60 years. When the cores were finally drilled and the data plotted, his curves were waiting. Not approximately waiting, the way a rough estimate might happen to land near the right answer. Waiting precisely, and in the way that a calculation lands when the underlying physics is correct. The ice core data, gathered from opposite ends of the Earth by researchers working decades after Milankovich's death, showed strong, clear responses at periods close to 23,000 years, 41,000 years, and 100,000 years. Deep sea sediments showed the same. Layered deposits of dust carried by ancient winds showed the same. When scientists in the latter part of the 20th century finally placed Milankovich's predicted curves beside the measured climate record, the alignment was not a suggestion or a rough correlation. It was a match. The ice itself had delivered a clear, almost elegant heartbeat, and the hidden gears that made it beat were the 3 rhythms Milankovich had named from a desk in occupied Budapest, and that is an achievement that is difficult to place in any ordinary category of scientific work. It belongs alongside the rare cases in which a theorist predicts the existence of something that instruments cannot yet detect, and then the instruments arrive, and the thing is exactly where the theory said it would be. The orbital gears are real. The timing they impose on Earth's climate is real. That part of the story is, as much as anything in the earth sciences can be, settled. But a gear arrangement that tells you when something will happen does not explain how powerfully it happens. And this is the gap that matters. The orbital cycles change the distribution of sunlight reaching Earth. They shift how much arrives at particular latitudes in particular seasons. But the total change in energy is small. The numbers, when worked through carefully, describe a gentle nudge, a modest redistribution, not the kind of forcing that, on its own, buries a continent under 3 kilometers of ice or drops global sea levels by enough to drain the seafloor and connect land masses separated by the open ocean. The timing, Milankovich explained. The sheer scale of the transformation he did not, because the orbital cycles alone are not sufficient to produce it. They are a skeleton, a precise, beautifully articulated skeleton. But a skeleton is not a living creature. To understand how tiny shifts in sunlight can transform the world, we need muscles, organs, and nerves. We need to understand the feedbacks. So what are the muscles? What are the organs and the nerves? Begin with the most visible one, the one you could, in principle, watch with your own eyes if you stood at the edge of a glacier and waited long enough. Begin with what happens to light when it lands on snow. Fresh snow is almost impossibly bright. If you have ever stepped outside on a clear winter morning after a heavy snowfall and found yourself squinting even before the sun was fully up, you have felt this. The surface of fresh snow reflects most of the sunlight that strikes it, bouncing it back upward, returning it to space rather than absorbing it and turning it into warmth. This property, how much of incoming sunlight a surface reflects rather than absorbs, is what scientists call albedo, and fresh snow has one of the highest values of any surface found on this planet. Compare it to the dark needles of a boreal forest, or the darker still surface of open ocean water, which absorbs most of the light that falls on it, and the difference is enormous. Where open ocean drinks in sunlight and warms, fresh snow spits it back. Where a forest floor covered in dark leaf litter, hoards heat, a snow-covered meadow refuses it. Now hold that contrast in your mind and think about what it means in a system that is already cooling. Suppose, through one of Milankovich's orbital nudges, northern summers become just slightly less intense than usual. Not dramatically colder, not the kind of cold you would necessarily feel as obviously wrong if you were living through it. Just enough that in some high-latitude regions, the snow that fell the previous winter does not entirely disappear before the first snows of the following autumn begin to arrive. In a normal year, summer sun would have cleared that snow away, baring the darker ground beneath, allowing the soil and rock to absorb warmth and radiate it back into the lower atmosphere. But in this slightly cooler summer, that clearing does not quite complete itself. Patches survive, and the patches that survive are bright. The following winter adds new snow on top of the patches that remained. Now, there is more snow going into the next summer than there was the year before. If that summer is also slightly weak, and if the orbital cycle is still in its gentle downward phase, it will be, then even more snow survives than the year before. The bright patch has grown. A larger area is now reflecting sunlight instead of absorbing it. And here is where the system begins to tighten into something that feels less like weather and more like mechanism. So the reflected sunlight that the growing snowfield sends back to space is sunlight that does not warm the region. A region that does not warm as much stays closer to the conditions that allowed snow to survive in the first place. More snow surviving means more reflected sunlight next summer. More reflected sunlight means less warming. Less warming means more snow surviving again. Each turn of the loop strengthens the next turn. The loop does not need any additional orbital push to keep tightening. It carries itself forward, amplifying the initial cooling through its own geometry. Bright surface, less heat, more bright surface, still less heat, until what began as a marginal nudge from a slightly different orbital configuration has become a self-sustaining expansion, spreading outward and upward, building mass and altitude and, with them, its own local climate that increasingly insulates the growth from the warmth trying to push back. This is what the word feedbacks means, in this context and in the climate system broadly. A feedback is not simply a consequence. A consequence is a one-time result. Push a button, a light comes on. A feedback is a consequence that loops back and changes the very condition that produced it. The warming or cooling that results from a feedback does not stop at the first step. It returns to the beginning of the process and alters it, which produces more warming or cooling, which returns to the beginning again. A positive feedback, positive in the mathematical sense, meaning self-reinforcing, takes whatever direction the system is already moving and amplifies it, compounds it, as pulls it further and faster in the direction it was already heading. The ice-albedo feedback is perhaps the most spatially dramatic positive feedback the climate system contains. And it has a geography. There is a latitude, around 65 degrees north, where the large land masses of North America and Eurasia sit waiting, at which the balance between summer warmth and winter snowfall is most delicately poised. South of there, summers are long and strong enough that almost nothing short of a full glacial climate would allow snow to persist year-round. North of there, the land is already cold enough that summer barely clears the snow even under ordinary orbital conditions. But right at that latitude, the system is perched at a threshold. It sits in a narrow band where summer warmth and winter snowfall are nearly matched, where the question of whether snow survives the season is not decided by a large margin, but by a small one. When northern summers weaken at that latitude, even by a modest amount, the balance tips. Snow survives that would otherwise have melted, and the moment it survives, the feedback engages. The loop begins to turn, and once the loop is turning, it does not need the orbital nudge to sustain itself any longer. The bright surface it creates becomes its own reason to persist and grow. Sit with that for a moment. A slight dimming of summer sunlight at a particular latitude. That is all the trigger requires. What follows from it does not require anything more, because the loop that survives that first winter propagates through its own logic, summer after summer, decade after decade, and building the kind of mass that can eventually press bedrock downward and fill valleys with 3 kilometers of ice. The orbital timing sets the clock. The ice-albedo feedback winds the spring. But surface brightness alone cannot explain the full glacial swing. The atmosphere itself is changing, thinning its own insulating blanket in ways that compound the cooling. And we have not yet looked upward at what is happening in the air above that growing ice. Stand at the edge of that growing ice sheet in your mind. The air is sharp and very dry. Dryness is not incidental. It is the second hand the system has just played, and it matters in a way that is easy to underestimate until you follow it to its conclusion. The atmosphere is not a neutral container. It traps heat partly because of carbon dioxide, which everyone has heard about, but also because of water vapor, which is less discussed and yet carries enormous weight in the thermal budget of the planet. Warmer air holds more water vapor. This is not a subtle relationship. It is a direct and powerful one. When air warms, it can carry more moisture, and that moisture acts as a greenhouse gas, trapping outgoing heat and sending some of it back downward to the surface. When air cools, the reverse is true. Cooler air holds less water vapor. The atmosphere becomes drier, leaner, thinner as a greenhouse blanket, and the heat that the surface radiates upward escapes into space more easily than it did before. So the cooling that began with a weakened summer and continued through the ice-albedo loop now reaches up into the atmosphere and begins pulling a second thread. Or the planet's own air becomes slightly more transparent to the heat trying to leave, and that transparency allows the surface to cool further, which reduces water vapor further, which allows even more heat to escape. This is another feedback, layered directly on top of the first, turning in the same direction, compounding what the ice-albedo loop already started. It helps to hold in mind what a greenhouse blanket actually does. The planet is constantly shedding energy. The surface warms in sunlight and then radiates heat back upward towards space, day and night, in a continuous process of release. The greenhouse gases in the atmosphere intercept some of that outgoing heat and redirect it. Without them, the planet's average surface temperature would be far below freezing, cold enough that the oceans as we know them would not exist. And the blanket is not a luxury. It is the reason liquid water is possible at the surface at all. Now picture that blanket developing thin patches, not tearing, not disappearing, but thinning, becoming less effective at holding the warmth in. The cooling that the ice-albedo feedback drives begins to thin the blanket by squeezing water vapor out of the air, and a thinner blanket means still more cooling, which means still thinner blanket. The feedbacks are not working separately. They are working together, each one making the conditions slightly more favorable for the next turn of the others. And then there is the ocean. The ocean covers most of the planet's surface, and it holds an enormous amount of dissolved carbon dioxide, far more than the atmosphere contains. The amount of carbon dioxide the ocean can hold in solution is not fixed. It depends, among other things, on temperature. Cold water dissolves more carbon dioxide than warm water does. If you have ever opened a cold carbonated drink and then left a second one on a warm counter for an hour before opening it, you have watched this principle in action. The cold one holds its gas under pressure with relative calm. The warm one, when you open it, pushes the dissolved gas back into the air quickly because the warm water cannot hold as much in solution. The ocean works on the same principle across an incomparably larger scale. As the climate cools and the ocean surface temperatures fall, the ocean's capacity to absorb carbon dioxide from the atmosphere increases, and carbon dioxide moves from the air into the water. The atmosphere loses greenhouse gas. The blanket thins from this direction too. But the ocean's role does not stop with simple dissolution. In the surface waters of the ocean, microscopic organisms, phytoplankton, draw carbon dioxide out of the water as they grow, fixing it into their bodies the same way a forest tree fixes carbon into wood. When they die, some of that carbon sinks with them into the deep ocean, carried out of contact with the atmosphere for centuries or longer. This is the biological pump, and during glacial periods, it appears to have run with unusual strength. Part of the reason involves dust. As ice sheets expand and the planet cools and dries, regions that were once lightly vegetated become bare and exposed to wind. Deserts grow, and the wind picks up fine mineral dust from those expanding deserts and carries it across thousands of kilometers, some of it falling into the open ocean. That dust contains iron. In many parts of the open ocean, iron is the limiting nutrient, the one ingredient in shortest supply that determines how much phytoplankton can grow. When iron arrives on the surface, plankton blooms respond. More organisms grow, more carbon is fixed, more carbon sinks into the deep water when those organisms die, and less carbon remains in the atmosphere above. The greenhouse blanket thins again, from yet another direction, driven by the same expanding ice and cooling temperatures that set the other feedbacks in motion. The orbital nudge that started this process is now almost invisible beneath the weight of everything it set in motion. The trigger has been buried by its own consequences. A slight dimming of summer sunlight at 65 degrees north was enough to allow snow to survive one extra season. And from that single survival, the ice-albedo loop engaged, and the water vapor feedback stacked on top of it, and the ocean began drawing down carbon dioxide through both the physical solubility effect and the biological pump. And the greenhouse blanket thinned from multiple directions simultaneously, and the cooling deepened and spread and reinforced itself with every passing cycle of the seasons. This is what a set of feedbacks doing the same work at the same time actually feels like from inside the mechanism. Not a single cause building to a single effect, but a convergence of reinforcing processes, each one making the others slightly more powerful. The whole system biased in one direction with a weight that increases as it moves. This also explains the shape of the signal that the ice cores record. That sawtooth pattern with its long, slow descents and its sudden, sharp recoveries. The cooling is gradual because the feedbacks compound one at a time, accumulating over tens of thousands of years, each layer of ice and each reduction in water vapor, and each drawdown of atmospheric carbon dioxide, adding its small contribution to the next. But the warming at the end of a glacial cycle moves differently. When orbital forcing eventually strengthens northern summers again, the same feedbacks that enforced the cooling begin reversing. But they reverse not one at a time. Slowly, in sequence, but in something closer to a cascade, each threshold crossed, making the next threshold easier to cross. The ice retreating and reflecting less sunlight, and warming the air and increasing water vapor and reducing the ocean's carbon hold, all in an accelerating sequence. The sawtooth is not symmetrical because the physics of accumulation and the physics of collapse are not symmetrical. Building an ice sheet requires overcoming inertia, kilometer by kilometer, decade by decade. Losing one requires only that the system tip past the point where its own self-reinforcing logic reverses direction, And now we need to watch what happens when these feedbacks have run their course and the planet has settled into a full glacial state. At that point, ice is no longer a feature of high mountain peaks and polar coastlines. It is a structural element of the planet, embedded in the landscape at a scale that changes almost everything about how the world looks, sounds, and functions. From space, a full Ice Age world does not look like the familiar blue marble you know. The blues and greens that dominate every photograph taken from orbit. The broad sweep of ocean, the dark smear of forest across continents, the thin wisps of cloud. Those are the colors of the world as it is right now, during a warm interval. In a full glacial state, those colors are replaced, but white pushes down from the north and spreads across enormous portions of North America and Northern Europe and Asia, not as a seasonal dusting that vanishes by April, but as a permanent structural feature of the planet's surface, as much a part of the land as mountain ranges. The planet you would see from above would look wrong in a way that is difficult to name precisely, familiar in its basic shape, but altered in a way that suggests something massive and slow has been at work for a very long time. Start with the ice itself. The Laurentide ice sheet, which covered most of North America during the last glacial maximum, was 2 to 3 kilometers thick across much of its extent. That number is easy to say and very hard to absorb. 2 to 3 kilometers is not a layer of ice on a road or a frozen lake. It is a solid mass of glacial ice whose base rested on the bedrock of the continent and whose surface rose higher into the sky than any structure human beings have ever built or are likely to build. The tallest buildings ever constructed reach perhaps half a kilometer into the air. The Laurentide ice sheet's surface, over the regions where it was thickest, would have been 4 to 6 times higher than that, rising into an altitude where the air is noticeably thin, where the cold is not the cold of a winter morning, but the cold of an environment that is genuinely hostile to unprotected human biology. If you stood at the base of that ice sheet and looked upward along its edge, you would not see the top, yet the surface would slope away from you and disappear into the sky long before your eye could follow it to its highest point. And this was not a vertical cliff, but a gradual rise. A surface that extended not for the length of a city block, or a valley, or a mountain range, but for thousands of kilometers in every direction. A continuous frozen landscape reaching from where the ice ended in the south all the way to the northern limits of the continent. Now, consider what that weight does to the ground beneath it. The crust of the Earth is not rigid in the way a tabletop is rigid. Over timescales of thousands of years, it behaves more like a very stiff, very slow fluid, capable of bending, pressing downward under a load, and eventually rebounding when that load is removed. Under the thickest parts of the Laurentide ice sheet, the crust was depressed by hundreds of meters. The bedrock itself was physically pushed downward into the mantle by the sheer mass of ice stacked above it. Hudson Bay, the enormous body of water in northern Canada, sits today at the approximate center of where the ice was thickest, and the crust beneath it has not yet fully recovered. It is still rising, millimeters per year, slowly returning toward the position it occupied before the ice arrived. Scandinavia is doing the same. The land surface of Norway and Sweden and Finland is still moving upward, still compensating for a weight that vanished more than 10,000 years ago. The ice is gone, but the Earth's interior is still responding to the memory of it. And the effects of that ice were not confined to the land directly beneath it. And the ice also redirected the continent's waterways. Rivers that once flowed in particular directions were blocked by advancing glaciers and forced into new channels. When the ice eventually retreated, meltwater accumulated in enormous proglacial lakes along the ice margins, And when those ice dams failed, the water released was not a flood in any ordinary sense of the word. In the region of what is now eastern Washington state, repeated catastrophic floods carved a landscape of scoured channels and dry waterfalls and strange boulder deposits that geologists now call the channeled scablands. A terrain so obviously shaped by catastrophic water that the scientist J. Harlan Bretz, who first proposed the flood hypothesis in the 1920s, was dismissed for decades before the evidence eventually became undeniable. The ice shaped the land not just where it sat, but everywhere its meltwater ran. Meanwhile, the lowering of sea level changed the map of the world at its margins. 120 meters of ocean drawn up into ice and held on the continents sounds like a number on a graph. But on a real coastline, it means something very concrete. The shallow continental shelves, which slope gently outward from most land masses before dropping away to the deep ocean floor, were dry. The North Sea, which today separates Britain from continental Europe and reaches depths of only 25 to 40 meters across much of its area, did not exist. In its place was a landscape of plains and river valleys and wetlands, a region now called Doggerland, and where the rivers Rhine and Thames and others met and flowed across dry ground before reaching a coastline that lay far to the northwest of where it sits today. Britain was not an island. It was a peninsula of Europe, and the land connecting them was inhabited. We know this because fishing trawlers working the North Sea floor have occasionally dragged up stone tools and the bones of animals that lived and died on that dry surface before the ice melted and the sea returned. In the east, the shallow Bering Strait between what is now Alaska and Siberia was not a strait at all. The exposed seafloor formed a land connection approximately 1,000 kilometers wide. Not a narrow crossing, but a broad, open region with its own weather patterns and its own vegetation, vast enough that the people who lived within it may not have experienced it as a boundary between two worlds, but simply as the world they inhabited. And the loess, the fine wind-blown dust scoured from the glacial outwash plains by the dry, powerful winds of the glacial world, settled across enormous regions of central China and eastern Europe and the American Midwest in deposits that are tens of meters thick in places, forming some of the most fertile agricultural soils on the planet today. A gift from a world of ice and wind that existed long before any farmer turned the first furrow. The glacial world was not only ice, it was also dust and redirected rivers and lowered seas and crust pressing downward under impossible weight. It was the whole planet rearranged. But this Ice Age world was not a barren wasteland, and beyond the ice sheets, a biome existed that has no modern equivalent. A grassland so vast and so productive that it makes the modern world seem ecologically impoverished. And yet, the word that keeps emerging when you look honestly at that world is not barren. It is not empty. The assumption runs deep. Ice Age, therefore cold, therefore lifeless. But the assumption is wrong, and the evidence against it is written in bone and pollen and frozen soil across 4 continents. Beyond the ice sheets, where the climate was cold but not glacial, dry but not desert, a biome existed that stretched from the Atlantic coast of what is now Spain all the way east across Europe and Asia, across the exposed floor of Beringia, and into what is now the Yukon in northwestern North America. It was, in the truest sense of the phrase, a grassland that wrapped nearly halfway around the planet, and it was one of the most productive ecosystems the Earth has produced in the last several million years. Scientists call it the Mammoth Steppe, and the name does some work, but it does not do enough. The word steppe suggests something thin and marginal, an afterthought of vegetation between more impressive biomes. The Mammoth Steppe was nothing like that. It was a vast, cold, dry grassland of extraordinary productivity. Not lush in the tropical sense, not soft or welcoming, but dense with the kind of tough, nutritious grasses and herbs that, in a cold climate, with long days of summer sun, support enormous standing crops of plant material and, through that plant material, enormous standing populations of animals. It was not a barren tundra, which is what a lot of people imagine when they picture the land beyond a glacier. Tundra today is wet and boggy, underlain by permafrost that traps water at the surface and prevents deep root growth. The Mammoth Steppe was drier, windier, and colder, but those conditions produced grass, not bog, and grass feeds grazers in a way that waterlogged tundra simply cannot. Close your eyes and let that landscape settle. A grassland so vast it wraps nearly halfway around the planet, thick with herds that rival anything Africa has today. This is not a dead world. It is a different world. The herds on that steppe would have stopped you where you stood. Woolly mammoths moved across it in groups, their long, curved tusks adapted for sweeping snow aside to reach the frozen grass beneath, as their dense layered fur insulating bodies that could weigh several tons. Alongside them moved woolly rhinoceroses, enormous animals carrying a double horn that has been found so well preserved in the permafrost of Siberia that researchers have examined the keratin itself. Giant bison with horn spans far wider than any bison alive today grazed in numbers that, judging from the fossil record, were simply staggering. Musk oxen, which survived to the present day in small numbers in the Arctic, ranged across much of the steppe in what were then unremarkable, typical, middle-of-the-herd populations rather than the relict survivors they are now. And the predators that evolved alongside these prey animals were matched to the scale of their quarry in ways that have no living parallel in the Northern Hemisphere. Cave lions, larger than modern African lions, hunted across the full extent of the steppe. Scimitar-toothed cats carried upper canines shaped for a killing technique that worked on the thick-necked megafauna of their world. Dire wolves ran in packs across the western reaches of this biome, and the bones they left behind have been found in extraordinary numbers in the tar seeps of what is now Southern California. Each skeleton a record of a predator that was perfectly built for a world that no longer exists. This was not poverty. This was, in the language that the planet breathes across long timescales, one of the great exhales of animal abundance, and the breath had shape and texture and life. Now place humans inside this landscape, because they were there. The genetic and archaeological evidence for when and how the first people reached the Americas has been one of the great ongoing puzzles of the last several decades, and one of the leading hypotheses for what happened turns on the geography of Beringia itself. The land bridge was not a narrow crossing, not a corridor that people dashed across during a brief window of opportunity. It was, as the evidence now suggests, a region roughly 1,000 kilometers wide, with its own climate, its own vegetation, and its own history. And the hypothesis that has emerged from the analysis of genetic lineages in indigenous American populations, a framework now often called the Beringian standstill hypothesis, proposes that a founding human population did not move directly from Asia to the Americas in a single rapid migration, but instead became isolated on or near Beringia for a substantial period, possibly several thousand years, while the ice sheets to the south and east blocked any further movement. To the east and south lay the Laurentide ice sheet and the Cordilleran ice sheet, which covered the mountains of western North America, and between them the passage that would eventually open was closed. The people who would become the ancestors of all indigenous Americans were not waiting at a door. They were living inside a room, a very large room, with tundra and steppe around them, and the sea to the north and the ice to the south. And they stayed in that room while the ice held its shape. The steppe near the ice sheet edges could endure 9 months of snow cover, which means winter was not a brief interruption, but a dominant condition that shaped every aspect of life. The food stored, the shelter built, the migrations undertaken, the animals followed. To live on the Mammoth Steppe, near the glacial margin, was to be embedded in one of the planet's long, cold exhales, to know its rhythms not as an abstraction, but as the organizing fact of every year lived. And then the warming came, the sharp spike at the top of the sawtooth. And this world, this entire biome, these herds, this way of life, began to unravel. The warming came, and it did not come gently. The Mammoth Steppe did not fade slowly and evenly into something else, the way a forest might shift its range over many centuries without any single generation noticing the change. What happened was fragmentation, the great connected sweep of grassland, that single biome running from the Atlantic coast of Europe across Asia and Beringia into the Yukon, began to break apart as warmth advanced from the south and moisture changed the character of the land. Where the steppe had been dry and cold and wind-scoured, conditions that kept the grass short and dense and nutritious, the warming brought more precipitation and different temperatures, and the vegetation that replaced the steppe, grasses, was not the same. Not in structure, not in nutritional content, not in the way it supported the animals that had evolved alongside it across tens of thousands of years. The herds that had moved freely across a nearly continuous expanse suddenly found themselves in fragments of suitable habitat, separated by expanding forests and wetlands and terrain that their bodies and their foraging strategies were not built for. The Mammoth Steppe did not shrink. It shattered, and the animals embedded in it, the mammoths, the woolly rhinoceroses, the giant bison, the cave lions, the scimitar-toothed cats, went with it. Not immediately, and not all at once, and the exact causes of these extinctions are still debated, because the warming was not the only thing happening at the same time. Human hunters were also moving through these landscapes, following the herds, and the question of whether it was climate or hunting, or some combination of the two that pushed the megafauna past the point of recovery, is one that researchers are still working through. What is not debated is that by the time the Holocene was well underway, most of the large animals that had defined the Mammoth Steppe were gone. The dire wolves were gone. The scimitar-toothed cats were gone. The woolly rhinoceros was gone. The mammoths persisted in isolated refugia for longer, with a small population surviving on Wrangel Island in the Arctic Ocean until roughly 4,000 years ago, long after the mainland populations had vanished. But even they did not hold. The breath that had carried so much life simply stopped. Now hold that image and pull back, because everything you have just followed, the build-up of the ice, the transformation of the landscape, the emergence of Beringia, the flowering of the Mammoth Steppe, the human populations moving through it, the fragmentation, the extinction, all of that is one tooth of the sawtooth, one cycle, one rise and one fall among 8 complete cycles visible in the ice core record, each of them roughly 100,000 years from beginning to end, and each of them carrying within it the same essential structure of loss and rebuilding and loss again. 8 times, something like the Mammoth Steppe assembled itself from the pieces available, and 8 times the warming came and broke it apart. 8 times, coastlines advanced across continental shelves as ice melted and sea levels climbed, drowning the exposed plains and shallows that cold periods had opened up. And then, when the cooling returned and the ice grew back, sea levels fell again, and the shelves emerged again. But not quite the same. Not with the same species, not with the same configurations of land and water and grassland and forest. The planet rebuilt, but it rebuilt from what was left. Ancient shorelines tell part of this story in a way that is easy to overlook. Along many coastlines around the world, there are raised beaches and wave-cut terraces sitting well above the current sea level. Old shorelines stranded by the complex oscillation of ice and water across hundreds of thousands of years, each one a record of where the sea stood during some earlier interglacial when ice had melted back and the oceans had filled. Some of those ancient shorelines are higher than the current sea level, because some earlier warm periods may have seen slightly more ice melt than the Holocene has so far produced. Each of those terraces is a record of a world that was briefly warm and then went cold again, of a coastline that existed for some thousands of years before the ice returned and the sea pulled back and the whole cycle reset. Stand on one of those raised terraces and you are standing on a ghost coast, a place where waves once broke and organisms once lived, and then the sea withdrew, and the land that had been submerged became dry again, and the organisms adapted or did not, and the cycle moved on without them. This is the weight that builds when you stop thinking about the sawtooth as a graph and start thinking about it as a repeated event. 8 times, so the planet assembled rich and complex ecosystems across wide latitudes and then disassembled them. 8 times, populations of animals expanded into new territory during the cold and then lost that territory when the warmth returned. 8 times, the landscape transformed so completely that an organism perfectly adapted to one phase would find itself maladapted to the next, its food source fragmented, its range compressed, the conditions it required moving faster than evolution could follow. And each cycle took roughly 100,000 years, which means the full 8 cycles in the ice core record stretch back across something close to 800,000 years of this repeated rise and fall. But the geological record goes deeper than the ice cores. The ocean sediments preserve climate signals across timescales far beyond what even the deepest Antarctic drilling can reach, because mud accumulates on the seafloor continuously, and in the right conditions, it preserves the chemical signals of past temperatures and ice volumes in the tiny shells of organisms that lived and died in the water above. And when scientists extended the record back past the 800,000-year mark visible in the ice, they found something that the pattern established over the last 8 cycles does not predict. The rhythm changes. Before roughly 1 million years ago, the dominant glacial cycle was not 100,000 years long. It was closer to 41,000 years. The same period as the obliquity cycle, the slow nodding of the Earth's axial tilt. The ice ages were still happening, is still paced by the orbital mechanics that Milankovich had calculated by hand in a Budapest apartment during a war. But they were coming faster, and they were somewhat less severe, and the 100,000-year pulse that feels so fundamental when you look at the last 8 cycles was simply not there. Something changed, somewhere around 1 million years ago, and the planet shifted from one rhythm to another. The geological record shows that the rhythm of these cycles has not always been the same. If you only looked at the last 8 glacial cycles, you might think the story has always been this way. But if you drill deeper into ocean sediments, past the 800,000-year mark, you see something surprising. The rhythm changes. But what caused that shift? What altered the fundamental pacing of the planet's largest climate oscillation? Is one of the genuinely open questions in the science of Earth's past, and the answer, when the evidence is followed carefully, turns out to say something unexpected about which part of the Earth system was actually keeping time. So the question becomes, what changed? The orbits did not change. The geometry of the solar system in the early Pleistocene was not meaningfully different from the geometry that governs the Earth today. Jupiter and Saturn were still pulling on the Earth's path around the Sun with the same slow gravitational rhythms. The eccentricity cycle was still running its roughly 100,000-year period. The obliquity cycle was still nodding the Earth's axial tilt through its 41,000-year range, and the precession of the poles was still spinning through its roughly 23,000-year wobble. Every gear in the orbital clock that Milankovich calculated by hand across hundreds of thousands of years was turning at exactly the same rate it had always turned. The cosmic clock had not been rewound or adjusted, and yet the planet's response to that clock shifted fundamentally, somewhere around 1 million years ago, crossing from one regime into another and never returning. Which means that whatever changed was not up there, in the orbital mechanics, but down here, on and in the Earth itself. The details of when exactly this shift began are still debated. Different studies produce somewhat different dates, but the essence is clear. Somewhere around 1 million years ago, the climate system crossed a threshold and never went back. So the transition appears to have unfolded gradually, somewhere between roughly 1.2 million and 800,000 years ago. Not as a single sharp event, but as a slow crossing from one mode of behavior to another. And the record before that crossing is coherent and consistent enough that we can say with confidence what the world looked like on the other side of it. From roughly 2.5 million years ago, when large-scale glaciation of the northern hemisphere first began in earnest, up through the approach to that threshold, the dominant rhythm of the glacial cycle was not the 100,000-year pulse that defines the last 8 cycles. It was the 41,000-year cycle, the obliquity period, the slow change in the degree to which the Earth's axis tilts toward or away from the Sun. And ice ages were coming and going nearly 2.5 times more frequently than they do today, and they were somewhat less severe. The swings between cold and warm were real, and they were large by any measure that matters to the organisms living through them. But the ice sheets did not grow quite as thick, the cold phases did not last quite as long, and the intervals between them did not stretch out across nearly 100,000 years of slow accumulation before the whole structure collapsed. The world was still cycling. It was still being paced by the orbital mechanics. But the instrument playing those mechanics was not the same instrument it would later become. One leading idea for what changed, and this is where the argument takes a turn that is genuinely surprising, even once you have followed everything else carefully, lies not in the atmosphere, not in the oceans, not in the orbital geometry, but in the ground, in the literal physical surface of the high-latitude continents. Before the Pleistocene ice ages began, the bedrock of northern North America, northern Europe, and northern Asia was covered by a deep layer of loose material, soil, gravel, fragmented rock, the accumulated product of millions of years of slow weathering and chemical breakdown. Geologists call this material regolith. It is not solid rock. It is the crumbled, softened, partially dissolved remnant of rock that has been broken down by water and temperature and time until it no longer holds together as a coherent mass. And in the early cycles of glaciation, when ice sheets advanced southward across those high latitudes, and they were advancing over this soft, loose material, they were pushing across something that did not offer the same resistance as the bedrock beneath it. Ice sheets sitting on regolith behave differently from ice sheets sitting on bare rock. They move differently. They slide more readily. And because the regolith is compressible and mobile in ways that solid rock is not, the ice sheet above it cannot build quite as high, cannot sustain quite as much mass, cannot resist the orbital warmth of a high obliquity summer quite as stubbornly. But each time the ice advanced, It did something to that regolith. It scraped it. It ploughed it southward, deposited it in moraines, mixed it into outwash plains, carried it in meltwater streams to places far from where it had originally formed. Each glacial advance stripped some of that soft material away and exposed the harder bedrock beneath. And then the ice retreated, and the next cycle came, and the ice advanced again, this time across a surface that had a little less regolith and a little more bare rock than it had the time before. And it stripped a little more, and it retreated again. And this process continued, cycle after cycle, for hundreds of thousands of years, each advance progressively removing more of the soft buffer between the ice and the underlying stone, until the high-latitude continental surfaces that had once been cushioned by deep regolith were instead scoured clean, the bedrock exposed and bare and offering the ice sheets a fundamentally different foundation to build on. This is where the feedbacks return, in a form that takes a moment to fully absorb. Because what happened to the regolith is not just a geological footnote to the climate story. It is itself a feedback. Not the kind that operates within a single glacial cycle, the way ocean temperatures and carbon dioxide and ice-albedo reinforce each other over thousands of years, but a feedback that operates across cycles, accumulating across hundreds of thousands of years, each cycle making the next one slightly more capable of severity. Ice on hard bedrock grips, differently than ice on loose soil. It cannot slide as easily. It builds taller under the same accumulation of snowfall because the base resists rather than yields. An ice sheet on exposed bedrock is, in a real mechanical sense, a more stubborn structure, harder to melt away, more capable of persisting through a warm summer or even several warm summers, and more capable of growing through multiple obliquity cycles without fully collapsing between them. And this is the key. Once the ice sheets became capable of surviving through one tilt maximum without disappearing, they could accumulate across 2 cycles, or 3, building to a size and thickness that required not just one favorable summer, but a rare alignment of multiple orbital factors before they would finally give way. The 100,000-year eccentricity cycle, which had previously been too weak to be the dominant pacer, became decisive by default, because only the largest and rarest alignments of orbital warmth were now sufficient to overwhelm ice sheets that had grown thick and stubborn enough to resist anything less. The Milankovich gears had not changed. The same orbital ticks that had always been there are running at the same frequencies, encoding the same slow rhythms in the amount of summer sunlight falling on the high northern latitudes. All of that was identical. But the Earth's response to those gears had deepened. The planet had, across hundreds of thousands of years of repeated glaciation, sandpapered its own high-latitude surface clean, and in doing so, had made itself capable of a kind of glacial cycle it had not previously been able to sustain. It changed its own rules. Not through any external forcing, not through a shift in solar output or a reorganization of the continents, but through the slow, cumulative mechanical consequence of its own ice advancing and retreating again and again across the same ground until that ground was transformed. The 100,000-year world that we think of as the fundamental rhythm of ice ages. The world whose signature runs through the Vostok cores and the Dome Sea record and the 8 great cycles of the last 800,000 years, is not the original setting of the system. It is what the system became after it had modified itself severely enough to make that kind of extreme oscillation possible. And we live inside it. We live inside the most extreme version of the glacial cycle the planet has yet produced. The version the Earth worked its way toward across more than 1 million years of incremental self-modification. which means that when an ice age in this regime ends, it does not simply ease into warmth the way an earlier, shallower cycle might have. When ice sheets this thick and this stubborn finally lose their grip, yet the consequences are not gradual. When the ice sheets of this deepened regime finally lost their grip, they did not release the world gradually. That is perhaps the most important thing to understand about the sharp right edge of the sawtooth, the edge that represents not just warming, but the end of one entire glacial world and the sudden convulsive beginning of another. The slow slope downward, the long cold accumulation across tens of thousands of years, was matched not by an equally slow recovery, but by something far more abrupt. The sawtooth's teeth have grown deeper since the Mid-Pleistocene Transition, and the spikes at the end of each tooth have grown correspondingly sharper, because the ice that had to be destroyed was thicker and more stubborn than anything that came before. And when it was finally destroyed, and it released energy that had been stored in the system for nearly 100,000 years all at once. Consider what happens to the carbon. Through the long, cold phase, the ocean had been pulling carbon dioxide out of the atmosphere, cold water dissolving more gas, the biological pump burying organic carbon in the deep, the whole system slowly starving the atmosphere of its insulating blanket. Carbon dioxide concentrations had fallen to somewhere around 180 parts per million at glacial maximum, low enough that plant growth was genuinely stressed across much of the land surface, low enough that the air was measurably thinner in its greenhouse warmth. And then, as orbital forcing finally tipped the system toward deglaciation, that carbon came back, not slowly, and not across the same timescale it had taken to accumulate in the cold, deep ocean. It came back in pulses, tens of parts per million within a few thousand years. A span of time that sounds long until you realize it is roughly the same duration as recorded human history repeated twice or 3 times over. The atmosphere was reinfused with its insulating layer at a pace that the Milankovich gears themselves had not directly caused. The gears provided the first nudge. The carbon did the amplifying, fast and hard, in a way that outpaced the orbital signal that triggered it. And the ice was not simply melting evenly at its edges the way a block of ice slowly shrinks on a warm day. The great marine ice sheets, the ones whose bases rested not on high ground but on bedrock that sat below sea level, grounded in basins under their own enormous weight, were vulnerable in a way that land-based ice is not. When the oceans began to warm, even slightly, that warmth reached the margins of the ice sheets from below. Seawater, heavier and more thermally energetic than the meltwater pooling at the surface, penetrated beneath the grounding lines where the base of the ice met the seafloor. It ate at the ice from underneath, melting the point of contact between the ice and the rock, causing the grounding line to retreat inward. And once the grounding line retreated, the geometry of the ice sheet changed in a way that accelerated its own collapse. More of the ice base was now floating freely in warmer water, exposed to the same undercutting that had already consumed the outer margin. This is not a gradual, linear process, and it has a threshold quality, a point past which the retreat feeds itself. Ice that had been stable for thousands of years could begin to give way quickly once that threshold was crossed. The meltwater that resulted did not simply raise sea level uniformly and leave the ocean undisturbed. It poured into the North Atlantic in episodes, surges of cold, fresh water from collapsing ice sheets, from drainage of vast proglacial lakes that had built up against ice margins and then broke through in floods of extraordinary scale. Fresh water is less dense than salt water. When it spreads across the surface of the North Atlantic in large volumes, it forms a layer that resists sinking. and the entire circulation of the North Atlantic depends on surface water sinking. The cold, salty, yet dense water of the far North Atlantic is what drives the overturning circulation, the deep conveyor that pulls warm surface water northward from the tropics and releases its heat into the atmosphere above northwestern Europe and the Northern Ocean. When fresh meltwater spread across that region, the sinking stopped, or slowed dramatically. The warmth stopped being delivered northward, and so during what should have been a period of rapid global warming, during a termination, while ice was actively collapsing and carbon dioxide was surging back into the atmosphere, parts of the North Atlantic region paradoxically cooled. The global signal was one of rapid warming. The regional signal, in the very area where enormous ice sheets were melting, could run in the opposite direction for centuries or longer. The terminations were not clean warmings. They were upheavals, full of internal contradictions, regions cooling while the planet warmed, ice collapsing while new cold water suppressed the circulation that would otherwise have hastened that collapse. The last of these great terminations ended roughly 11,000 to 12,000 years ago, when the conditions that define our current world finally stabilized. The Laurentide ice sheet, which had once pressed down on the continent from Hudson Bay to the Appalachians, was gone. Sea levels had risen by roughly 120 meters. The carbon dioxide that had been locked in the cold, deep ocean had largely returned to the atmosphere. The North Atlantic overturning circulation had re-established itself. The broad outlines of the climate system we inhabit now were in place, and the Milankovich gears, the same orbital mechanics that Milutin Milankovich calculated by hand in a borrowed apartment in Budapest, had provided the trigger, as they always had. But what those gears now set in motion was a response from an Earth that had made itself capable of extremes far beyond the gentle 41,000-year rhythms of its earlier Pleistocene life. So here is where we stand. The sawtooth, with its deep cold slopes and its sharp warm spikes, tells us that the world we live in is positioned on one of those spikes. The warmth we call normal is the brief vertical rise at the end of a nearly 100,000-year descent. And the question of how long we remain on that spike and what forces are now acting on it is no longer a question about orbital mechanics alone. The question of how long a warm period lasts is not answered by how warm it feels from the inside. From inside the Holocene, the climate feels essentially permanent. The seasons have a rhythm. The monsoons arrive. The glaciers that exist are where they have always been by any measure of living memory or written record. The world seems to have settled into a condition of reliable, if varied, stability. And in a certain strict sense, it has. The Holocene is genuinely unusual in the ice core record. Over the last 800,000 years, interglacials have typically been brief and often uneven, marked by secondary cold pulses and rapid swings in temperature that made them more like volatile reprieves than true stability. The Holocene is different. For roughly 10,000 years, global average temperatures have fluctuated within a range of only about 1 to 2 degrees Celsius. Not 10 degrees, not 5. 1 to 2. There have been cooler periods and slightly warmer periods. Regional variations, shifts in monsoon patterns, fluctuations in alpine glaciers. But the broad thermal envelope within which all of this variation happened has remained extraordinarily narrow by any comparison the ice cores can offer. To understand how narrow that is, you need to hold the other number beside it. The full temperature difference between the depth of the last glacial maximum, when the Laurentide ice sheet stood 2 to 3 kilometers over Hudson Bay and sea levels were 120 meters lower, and the warmth of the modern world is roughly 5 to 6 degrees Celsius. That is the full swing of the sawtooth. And that is the difference between ice burying the northern third of North America and the world you know. 5 to 6 degrees across nearly 100,000 years of rise and fall. And within the warm spike at the top of that range, human civilization has operated inside a variation of 1 to 2 degrees. The entire thermal range that separates the conditions under which agriculture becomes possible from the conditions under which it fails sits within a fraction of the full planetary swing. It is as though the sawtooth spent nearly 100,000 years sweeping from the floor to the ceiling of a tall room, and then settled, for 10,000 years, into a trembling of only a few centimeters near the top. Everything fits inside those few centimeters. The first permanent agricultural settlements in the Fertile Crescent, beginning perhaps 10 to 11,000 years ago, emerged at the very opening of this window. The domestication of wheat and barley, of cattle and sheep, the slow transformation of mobile foraging communities into villages and then into towns. All of that happened in the Holocene Plateau. The first cities, rising along the rivers of Mesopotamia and the Nile and the Indus, emerged within this plateau. Every writing system ever devised, every legal code, every dynasty and republic and empire, every philosophical tradition and scientific revolution, all of it occurred within the same narrow band of 1 to 2 degrees of thermal stability. Not before it, not outside it, within it. And not just within the Holocene as a broad concept, but concentrated mostly within the last 5 to 6,000 years, which is the more recent half of a window that is itself a thin spike at the top of a long, cold descent. Recorded history, in any form that could be called history, fits inside a slice of time that the ice cores would barely register. This is what makes the Holocene so difficult to hold in the mind properly. Because the stability is real. It is not an illusion or a misreading of the data. The Holocene is, measurably, the most settled climate interval in the deep record. A plateau where the variation is genuinely small and the conditions genuinely benign for the kind of complex, dense, agriculture-dependent societies that define what we mean by civilization. But stability is not the same as permanence, and the same orbital mechanics that paced the last 100,000 years of ice did not stop calculating when the Holocene began. Is summer sunlight reaching 65 degrees north latitude, the same critical latitude where the feedbacks that end ice ages are thought to be most sensitive, has not been constant across the Holocene. In fact, it peaked thousands of years ago, early in the interglacial, when orbital geometry was still delivering maximum summer energy to the northern high latitudes. Since then, it has been declining, slowly, steadily, and in a direction the ice core record knows how to recognize. Precession has been carrying Earth's northern hemisphere summer away from the orientation that maximizes solar intensity at that latitude. Obliquity has been shifting. The orbital skeleton of the climate system, which drove the cooling phases of every previous cycle, has been moving in the direction it always moves at this point in the cycle. The summer insolation at 65 degrees north, which is arguably the most important single number in the pacing of ice ages, has been pointing downward for thousands of years. The planet has been receiving the same kind of slow signal it received at the onset of previous glacial periods, and the climate record shows that the Earth was, in some regions, beginning to respond. Glaciers in the Alps and Scandinavia began to regrow. Tree lines crept downward. The planet was leaning, very slowly, back toward cold. The planet was leaning back toward cold. That is not a metaphor or an interpretation. It is what the evidence shows. The cooling signal that was detectable in the behavior of glaciers and tree lines during the Middle Holocene continued, in fits and starts, into the period historians sometimes call the Little Ice Age. which ran roughly from the 1400s through the 1800s. During those centuries, alpine glaciers in the Alps and in Scandinavia advanced down their valleys to positions they had not occupied in thousands of years. Rivers in northern Europe froze with a regularity that startled the people living along them. The Thames froze hard enough to hold markets on its surface. Harvests in the northern latitudes became unreliable in ways that destabilized societies. The planet was not plunging into a full glaciation. It was nowhere near that. But it was doing exactly what the orbital pattern would predict it should do at this point in the cycle. The long downward lean that begins every glacial period was underway. Slow, early, and quiet, but underway. The Milankovich gears were turning in the direction they have always turned at this phase of the cycle, and the climate system was, however faintly, beginning to follow. Without any other force acting on the system, the models that simulate future climate using only natural orbital forcing suggest that this trend would have continued. The cooling that was already detectable in the neoglacial record would have deepened across thousands of years, interrupted by temporary reversals, but pointing, overall, in the direction of cold. The next major glacial inception, the point at which ice sheets would have begun to grow in earnest across northern Canada and Scandinavia, where ice sheets always grow first, is estimated at perhaps 50,000 years from now, but possibly somewhat earlier depending on the sensitivity of the models and the precise orbital configuration. That is an enormous span of time by any human measure. It is 10 times the length of all recorded history. It is 5 times the length of the entire Holocene. But in terms of the planetary rhythm we have been tracing, 50,000 years is not particularly far away. It is the next beat of the metronome. The system was tilted toward it, and absent any disruption, it would have arrived. Now hold that picture steady in your mind, because this is where the graph breaks. For 800,000 years, every cycle in the ice core record, every glacial and every interglacial, every rise and every fall of the great sawtooth curve, the concentration of carbon dioxide in the atmosphere oscillated within a band. At the cold end of each cycle, it dropped to around 180 parts per million, stressing plant life across the land surface. At the warm end, at the peaks of interglacials, at moments like this one, it rose to somewhere near 270 or 280 parts per million, perhaps approaching 300 at its highest. That upper boundary held for every cycle in the record. 8 complete cycles, 8 full oscillations across 800,000 years. The ceiling of the band sat at roughly 300 parts per million, and the climate system never pushed through it. Every warm period eventually pulled back. Every interglacial eventually gave way. The ceiling held because the feedbacks that govern CO2, the ocean dissolving and releasing it, the biological pump storing it in the deep sea, and the ice reflecting sunlight and keeping temperatures from climbing further. All of those processes kept the system cycling within the same range. The band was not a coincidence. It was the operating range of the planetary climate system as it had been configured for nearly 1 million years. Industrial fossil fuel burning has pushed atmospheric CO2 past 400 parts per million. Every oscillation, every glacial cycle, every warm spell that preceded us stayed within those bounds. In a geological instant, we have left them behind. Not gradually nudging toward the upper edge of the band, past it, by a margin that has no analogue anywhere in the 800,000-year record that the ice cores contain. The line that spent nearly 1 million years rising and falling within a fixed range has departed from that range entirely, and it has done so in a period of time so short that on the scale of the ice core graph, it would appear as a vertical line rather than a curve. It would not look like a variation within the pattern. it would look like the pattern ending and something else beginning. And this is where the orbital mechanics become almost poignant in their continued precision. The Milankovich gears are still turning. Precession is still slowly rotating Earth's orientation in space. Obliquity is still nodding the planet's axis through its long, slow cycle. The summer insolation at 65 degrees north is still declining, still pointing in the direction it has pointed at this phase of every previous cycle. But the system is no longer listening. Yes, so the CO2 concentration that now blankets the atmosphere is high enough that the cooling signal from orbital geometry cannot overcome the warming effect of the enhanced greenhouse. The subtle downward push that would, over tens of thousands of years, tip the balance toward renewed ice growth has been reversed. The neoglacial trend, the creeping advance of glaciers, the slow descent of tree lines, all of that has been halted and pushed back. The next ice age, which the orbital calendar had tentatively scheduled and which the climate system had already begun drifting toward, has been cancelled, or at minimum delayed by a span of time that climate models describe as hundreds of thousands of years, which is to say, beyond the horizon of anything we can meaningfully call planning. The question is no longer when the next ice age will come, and it is what form this long human-made summer will take. And the answer depends on the same feedbacks we met earlier. Only now, they are working in the other direction. And the feedbacks that made ice ages possible are still there. They did not switch off when the orbital geometry changed. They did not disappear when the CO2 concentration climbed past the band it had held for nearly 1 million years. They are the same feedbacks, the same physical relationships between ice and light, between ocean temperature and dissolved gas, between atmospheric moisture and the warming of the surface, and they respond to forcing in both directions with equal unthinking efficiency. The system that was so relentless at amplifying cooling is just as relentless at amplifying warming. That is the symmetry at the center of this. It is almost elegant, and in the way that something indifferent to human outcomes can still be described as elegant. Start with the ice. When glaciers grew, the process reinforced itself through the ice-albedo feedback. More ice meant more reflected sunlight, which meant less absorbed heat, which meant more ice. The same mechanism works in reverse with the same precision. As ice retreats, the surfaces it uncovers, dark rock, open ocean, saturated tundra soil, absorb sunlight that the ice was reflecting back into space. Each square kilometer of ice that disappears is replaced by a surface that holds heat instead of rejecting it. Warming drives retreat, and retreat drives more warming. And because ice sheets are vast, and because they do not melt uniformly, but in pulses and accelerations, the feedback does not proceed at a steady, gentle rate. It gathers. Yes, in the Arctic Ocean, which for most of the last 1 million years was insulated beneath sea ice through all seasons, now opens in summer and absorbs solar energy for months at a time, warming the water, which delays the return of winter ice, which extends the open season further, which warms the water more. The polar regions warm faster than the global average, and this is not an anomaly or a surprise. It is the ice-albedo feedback, working in the direction of warmth instead of cold. Then there is water vapor. The same atmospheric physics that made warm, moist air a greenhouse amplifier during glacial terminations applies now. Warmer air holds more water vapor than cooler air, and water vapor is itself a potent greenhouse gas. As the surface warms, evaporation increases. The atmosphere becomes more humid, and that additional humidity traps more outgoing heat, which drives further warming, which drives further evaporation. This was always part of the warming signal at the end of each ice age, tucked inside the larger story of rising CO2 and retreating ice. Now, it is operating in a baseline atmospheric state that is already warmer and moister than at any point in the 800,000-year record. The feedbacks are not starting from a neutral position. They are layered on top of an initial condition that is already above the upper edge of the ancient band. And then there is the permafrost. Across the high latitudes of the northern hemisphere, across Siberia, across northern Canada, across Alaska, there are soils that have been frozen for thousands of years, in some places for tens of thousands. Inside those frozen soils is organic material, dead plant matter, ancient carbon, biological residue from the mammoth steppe, and the forests and the marshes that preceded it, locked in the cold and unable to decompose. When permafrost thaws, that organic material becomes available to microbial life, which breaks it down and releases it as CO2 and methane. Methane is a considerably more potent greenhouse gas than CO2 over short timeframes. And the permafrost is thawing. The estimates of how much carbon is stored in permafrost soils are large enough to be consequential on a planetary scale. Enough, if released substantially, to add a meaningful additional push to warming that no human policy instrument can directly control. This is a feedback rather than a source we are managing, which means it does not respond to negotiations or agreements. It responds to temperature. When the temperature crosses thresholds, it releases carbon. That carbon raises the temperature, which thaws more permafrost. At the same time, the forests that cover large parts of the mid-latitudes, and which have for most of the Holocene acted as carbon sinks, pulling CO2 out of the atmosphere through photosynthesis and locking it in wood and soil, begin under high warming scenarios to shift from sinks to sources. Heat stress, drought, fire, and the migration of pests and pathogens push tree mortality upward in regions that were never adapted to those pressures. Dead and burning forests release their stored carbon back into the atmosphere. The biological pump that was slowly but reliably drawing carbon downward runs in reverse. And while forests are not as immediate or as mechanically certain as permafrost, they cover enormous areas. Climate zones, under the projections that follow from continued high emissions, may shift poleward by hundreds of kilometers over the course of centuries. Not the tens of thousands of years over which the mammoth steppe migrated, but within a span that ecosystems accustomed to gradual change have no obvious mechanism to track. The sawtooth pattern that the ice cores revealed, that slow, grinding descent into cold followed by the abrupt lurch back into warmth, always had the same basic shape, the same asymmetry, the same ceiling. In every one of those 8 cycles, the warm spike was brief and self-correcting. But what the feedbacks are now running toward is not a spike that corrects. They are running toward a sustained state, as a plateau or something worse, shaped by forcing that has no natural analogue in the record we can read. The sawtooth had a top edge because the system always ran out of warming momentum before it could push past 300 parts per million. That constraint is gone. And what replaces it, under scenarios where warming continues substantially, is sea level behavior that is difficult to contemplate without stepping back from it. The ice sheets that remain, Antarctica and Greenland, are enormous reserves of frozen water. The full melting of both is not a realistic near-century projection, but it is a physical reality that becomes relevant over the longer timescales the feedbacks operate on. If the warming forcing is sustained and the feedbacks amplify it in the ways they are understood to do, yet the eventual sea level contribution from major ice sheet loss could reach many tens of meters, not incrementally across a weekend, over centuries and millennia. But that distinction, while real, does not reduce the significance of the number. Every coastline on the planet is drawn at the current sea level. Every river delta, every port, every low-lying plain where river sediment built up over the last several thousand years, all of that was shaped by a sea level that the current CO2 concentration can no longer guarantee. The map of the world that we treat as geography is, in a longer view, a snapshot of one particular moment in an ongoing negotiation between ice volume and ocean surface. We have changed the terms of that negotiation. You might wonder whether Earth has ever experienced conditions like this. The answer is yes, but you have to look far back, to a time before ice sheets existed at all. The Earth has done this before. That is not a small thing to say, and it deserves to be held carefully rather than rushed past. When the previous warmth of an interglacial is offered as context, it does not quite capture what we mean when we ask whether the physics of a much warmer world is even possible. So look further back. Look not at the ice core record, which reaches 800,000 years into the past, but at the rock record, which reaches much further, and which preserves evidence of a planet that looked and functioned almost nothing like the one we know. In the Middle Pliocene epoch, roughly 3 to 5 million years ago, global temperatures were perhaps 2 to 3 degrees Celsius warmer than the pre-industrial baseline. Its sea levels were substantially higher than today, likely by somewhere between 10 and 25 meters, in part because ice sheets that now sit reliably on Greenland and parts of Antarctica were smaller or absent. That was not an anomalous spike. That was a sustained state lasting millions of years, with CO2 concentrations in the atmosphere that some estimates place at around 300 to 400 parts per million, a range that is, by now, familiar from a different direction. The Mid-Pliocene is, in a sense, the nearest geological analogue we have for the atmospheric chemistry we have already created. The climate of that world has not yet fully caught up to the chemistry we have produced, because the climate system responds slowly, because ice sheets do not melt in a decade, because the ocean absorbs heat over centuries. But the Mid-Pliocene is where the physics points, and if you look further back still, to the early Eocene, roughly 50 to 55 million years ago, the planet was something that would be almost unrecognizable from above. There were no permanent ice sheets anywhere on Earth. The poles were forested. Crocodiles and palm trees lived at latitudes where now there is permafrost and tundra and long polar winters. Average global temperatures were perhaps 10 to 15 degrees Celsius above what we would call normal, and sea levels were higher by many tens of meters because the water that is now locked inside the Antarctic and Greenland ice sheets was instead in the ocean. The planet was not dead. It was not uninhabitable in some absolute sense. It was simply organized differently, with different coastlines, different vegetation belts, different atmospheric circulation patterns, and no ice at either pole. The physics does not forbid a hothouse Earth. It has produced one before, repeatedly, across geological time, and the mechanisms that create it are not exotic or unusual. They are the same mechanisms, running further and longer in the same direction. What has never happened before, not in any record we can read, not in any transition the geology reveals, is the speed. The early Eocene warm period developed over millions of years, shaped by volcanic outgassing, by continental configurations, by the slow drift of tectonic plates repositioning land masses and ocean currents across tens of millions of years. Even the Paleocene-Eocene thermal maximum, a sharp warming event roughly 56 million years ago that is sometimes compared to what we are doing now, and involved a release of carbon that likely unfolded over thousands of years, and it is considered among the most rapid warming events in the geological record prior to this one. we have produced a comparable carbon release in roughly 2 centuries. The warming signal we are adding to the atmosphere is not geologically slow. It is, by any standard the rock record offers, nearly instantaneous. The state may have precedent. The speed does not. But here is something the planet will do, given enough time, that deserves to be said, even though it offers a particular kind of comfort that is difficult to feel directly. There is a process called silicate weathering, and it has been operating continuously for billions of years, quietly regulating the deep carbon cycle across timescales that make the Ice Age cycles look brief. Yes, or when silicate rocks, the hard, mineral-rich crustal material that makes up the bulk of Earth's continents, are exposed to rain and air, they react chemically with CO2 dissolved in water. The carbon is drawn out of the atmosphere, carried by rivers, and eventually deposited as carbonate minerals on the ocean floor. Over hundreds of thousands of years, and over millions of years, this process acts as a planetary thermostat. When CO2 is high and temperatures are warm, the hydrological cycle intensifies, rainfall increases, weathering accelerates, and more carbon is drawn down. Slowly, over immense stretches of time, the excess is consumed by the rock. This is not a rapid correction. It is not something that operates on centuries or even millennia in any meaningful way for the warming already set in motion. But it operates, reliably, and persistently, across the kind of time the planet thinks in. The CO2 we have added will not stay elevated forever. The question is only how long, and the answer is hundreds of thousands to millions of years. And once the CO2 declines enough, once the greenhouse blanket thins back toward concentrations the planet's orbital mechanics can work with, the Milankovich gears will resume their old role as conductors of the climate. The eccentricity cycle, the obliquity cycle, the slow wobble of precession. They have not stopped. They are turning now, as they turned through every one of those 8 cycles the ice cores preserved, as they turned during the Eocene and the Pliocene, and every warm and cold interval the rock record contains. The cosmic clock is still there, waiting behind the curtain of CO2, indifferent to what we have done to the surface of the planet, ticking on the same schedule Jupiter and Saturn have kept for billions of years. When the chemistry finally allows it, those cycles will once again find purchase on the climate system. Ice ages will resume. The slow descent will begin again. On the far side of an interval that is, from where we stand, essentially unimaginable in its length, the planet will return to a rhythm recognizable from everything described here. That is the reassurance. It is real. And it is, from where you and I are standing in the middle of the only centuries we will ever know, nearly impossible to feel as one. Stand for a moment in the middle of this strange place we have reached. Behind you, if you turn and look back across everything described here, you can see ice sheets grinding down through Hudson Bay, dust clouds sweeping across frozen Europe, sea levels falling as water locked itself into glaciers 3 kilometers deep, and then the long, slow thaw that gave human civilization the only window of stability it has ever known. 11,000 years of warmth, and in that warmth, wheat and barley domesticated in the Fertile Crescent, cities rising along the Euphrates and the Nile, and eventually the entire recorded architecture of human thought and culture, all of it fitted into an interglacial that was itself just one brief pulse in a rhythm that had been running for nearly 1 million years before any of it began. That is what is behind you, and ahead, stretching into a future that chemical weathering will eventually reclaim for the orbital cycle. It is an interval of warmth, unlike anything the Milankovich gears would have produced on their own. An interval shaped now partly by what 8 billion people have released from ancient rock and burned into the sky. Somewhere in the rock forming beneath us right now, in sediments accumulating on the floors of shallow seas and in the fine-grained layers building up at the mouths of rivers, there is a record being made of this moment. Future geologists, whatever form they take, will find it as a thin but unmistakable layer. The carbon locked in fossil fuels carries a distinct isotopic signature, lighter than carbon cycled through the living world, and that signature is now moving through the atmosphere and into the ocean and into the shells of organisms and into the sediment they leave behind. Alongside it will be traces of plastics, particles small enough to travel in ocean currents to every corner of the planet, settling into the record as a kind of mineral that never existed before in the history of the Earth. Alongside those will be concrete, industrial metals, the particular chemical fingerprints of a civilization that learned to extract and transform materials at a scale no biological process had ever managed. This is what geologists already call the Anthropocene. Not a formal accusation, but a simple geological description of the fact that one species has left a mark on the physical record of the planet that is as legible as the boundary layer that marks the end of the dinosaurs. A thin stripe in the stone. Fingerprints pressed into the sediment of an entire world. Between them is the thin slice of time in which you are alive, and the only moment where both the ancient rhythm and the human override are visible at once. You are alive at the precise junction where the ice core record ends and the new record begins, where the sawtooth graph of 8 glacial cycles gives way to a line that rises off the chart, where the planet's long breathing, the slow accumulation of ice over 90,000 years, the rapid gasp of termination, the brief warm exhale of interglacial, continues, but altered now in ways that the orbital mechanics alone would never have produced. We can trace the ice ages back 800,000 years in those Antarctic cores. We can see the CO2 rising and falling like a tide, never above 300 parts per million in all that time, never below 180. And we can see how our engines and our agriculture are now part of that breathing. The planet is still breathing. We have simply changed the rhythm of the breath. The cosmic metronome that once told Earth when to freeze and thaw is still ticking. The eccentricity of the orbit is still being nudged by the gravity of Jupiter and Saturn, the same way it has been nudged for billions of years. The axial tilt is still cycling through its slow arc. The wobble of precession is still turning, still shifting, which pole leans toward the sun in which season. None of that has stopped, and none of it is affected by what happens on the surface of this small planet in the outer arm of an unremarkable galaxy. We have simply layered our own beat on top of it. The silicate rocks are still being rained on. The carbon is still being drawn down, molecule by molecule, into carbonate minerals on the ocean floor. Across hundreds of thousands of years, across millions of years, that process will do what it has always done, and the CO2 will come back down. And when it does, the orbital gears will find purchase again, and the ice will return, and the planet will resume the rhythm preserved in those cores. That is not comfort for the centuries ahead, but it is true, and the truth of it says something about the kind of system we are part of. Old beyond any useful imagining, resilient across timescales that make our entire presence here look like a single line in a very long book. What is strange and worth sitting with as you drift towards sleep is that the thing that makes this moment so consequential is not merely the scale of what we have done to the atmosphere, and it is that we know we have done it. No other force in Earth's history that altered the planetary carbon cycle did so with awareness. The asteroid that closed the Cretaceous did not know what it was doing. The volcanoes that built flood basalts across Siberia and released carbon across tens of thousands of years did not make a calculation and choose a different path. We have built instruments sensitive enough to read the climate record of 800,000 years in compressed ice, calculated the orbital mathematics of a planet being pulled on by gas giants hundreds of millions of kilometers away, traced the isotopic signature of our own emissions into the shells of organisms living at the bottom of the sea, and understood clearly what that signature means. Whether that new rhythm becomes a brief noise or a long-lasting theme is, for the first time, partly up to us. Thank you for listening. Sleep well.